I want to introduce a friend of my extended Commodore family, but from there he went on to Apple and Microsoft and lots of other competition, we call him. My friend, Bob Welland.
Bill asked me to do a talk, and I kind of got the fantasy that I would kind of try to talk through Moore's Law as it happened in my career, because it's just kind of interesting. It gives you a little insight into what these products ended up being. So I'll just get started. But I wanted to start a little bit before me and a little bit before Moore, because it kind of gives you context. This is my only fancy shot in the whole slide. This would be Bell Labs, of course. And in 1947, there's one transistor. I think that's 75 years ago. It's kind of good to reflect on, like, we're infested with transistors now, and there was a time when there was one. It was not a great transistor. It was a point contact transistor. It wasn't great it was hard to make. I think one company tried to manufacture point contact transistors. It didn't work very well. But remarkably, and it was a transistor, it had, some gain and a frequency response. And in the next 10 years, a lot of really interesting stuff happened. They switched immediately to the junction transistor, and then they started trying to figure out, how do you make manufactured transistors? This diagram actually shows what's called an alloy junction transistor, where they squirted acids at the side and made this circular arc and then put indium in infill. I only put this up not because this was a good idea, but because there were a lot of ideas that people had to work their way through. And kind of remarkably, in the subsequent 10 years, you see the base width going from this pretty uncertain 25 to 50 micrometers down to 1 10 years later, where the frequency response goes from 10 megahertz to a gigahertz. So this is before Moore. This is just people trying to figure out, how do you make transistors? Of course, the last thing on that list is the planar transistor, and that's where the magic starts, right? This is the Fairchild. This is a flip-flop from 1960. It's the planar process, and the planar process is what leads to Moore's Law. Now, at first time I saw Moore's Law, this is from the paper, you say, oh, he's got 4 data points and he's drawing a line. That doesn't make any sense, right? I mean, it's exponential growth. That's crazy to claim that you could get some rational thing from 4 points. What I think Moore was thinking was, they figured out how to use lithography in the process technology. He could intuit that the silicon wafers are going to get more pure, that the process, the plants are going to have fewer imperfections in them, that the optics are going to get better. And so I think he was really looking at the planar process and saying, there's no obvious upper limit on how far this goes. And of course, he turned out to be mostly correct. I'm going to switch just for a moment before I go to things that have lots of transistors to talk about myself just briefly, and then about something that inspired me. So I grew up in Evanston, Illinois. This is an aerial photograph of Northwestern University. I grew up right there, and my dad, who was a professor of mathematics, worked there. And it was strange to wake up every morning with my dad sitting on the couch doing mathematics, go to school, come home, my dad sitting on the couch doing mathematics. And that's what I thought a career or job would be, and I never got to experience that. I bring him up because he had this. He had this Sony radio. When I was a kid, I took everything apart. And there was one thing I couldn't take apart because the consequences would have been severe, and that is this radio. But on the side of this radio, it said 9 transistors. And I was 8 years old, and I was like, what's a transistor? Why are there 9 of them? I wish I could take this apart. And it's interesting to reflect that, like, this was where transistors were, right? If you would have a car radio, you would have a transistor radio. Television still had tubes. Transistors were expensive, so you only put them in things that had an advantage of their size. But if you do the math, it's kind of interesting. There's, in 1969, probably 60 million families in the United States. So if they all had one of these radios, there's 600 million transistors in the United States used in consumer products, like less than a million. And if you think about your phone or anything, that's like a tiny, tiny number. And then to put it in contrast, 3 blocks from my house is the Vogelbach Computing Center. They had a CDC 6400, which was the little brother to the 6600, which was at the time the fastest commercial computer in the world. And it was about 400,000 transistors. So the whole consumer products in the United States has got 600. This thing has 400 just sitting there in this beautiful room. This picture is of a friend of mine, Dave Slate, who had the best chess program in the world for most of the 1970s. He was one of the few people who got to sit in front of that fantastic dual circular displays that the CDC 6000 series came with. And when I was doing research for this talk, I came upon this, which is a little essay by none other than George R.R. Martin, who went to Northwestern. And he was a very good chess player, apparently, and he thought computer chess was absurd. And I will read just a couple of sentences. And Northwestern CDC 6400 was a chess player, a bad one, a fish. During the years of tournament play, the machine earned not the title not once, but several times. A whole legion of human opponents regularly blasted the machine off the board. Then one day, during the summer of 1970, the fish became a champion. It happened in New York City during the 25th annual convention of the Association of Computing Machinery. Meeting at the New York Hilton Hotel, the ACM decided to enliven its proceedings with the world's first all-computer chess tournament. 6 competitors swam to the surface for the 3-round event, including programs from sites as distant as Texas and Alberta, Canada. Among the 6 was Chess 3.0, Northwestern's electronic fish. And if you've ever played chess, a fish is not what you want to be called. So in high school, of course, I owned one of these calculators like a gazillion other people, and now we're seeing Moore's Law starting to work. There's thousands of transistors in this magic TI chip that apparently Commodore bought for some of their calculators, maybe a precursor to this. This was one of 2 chips. The second chip was just a ROM. I don't know how many transistors are in this exactly, but you're starting to see, you know, that's not 9 transistors. I worked in high school at a place called Itty Bitty Machine Company, which was probably the second computer store in the United States. There's probably a lot of second computer stores in the United States. This one happened to be founded by none other than Ted Nelson, who wrote this very bizarre book called Computer Lib, which if you've never read it, you should read it. It's strange, but everyone owned it. Bill Gates republished it 15 years ago because it inspired him. And this is the catalog for Itty Bitty Machine Company. And when we moved into a new building, we plastered this poster over all the windows and scared people, apparently, because they thought, what does computers arise actually mean? It didn't really mean very much. So I built a lot of these early computers, the S100 machines, IMSIs, Processor Technology, Z, the Chromemcos, all came as kits. And no one wanted to buy a kit. So as a high school student, I put a bunch of these together and made a good living. I got like $50 for building one. Some poor sap thought he'd do it himself. He thought on a resistor where it has the leads that all of the lead was important, and so all of his parts were 1.5 inches off the printed circuit board because he didn't want to cut the special leady stuff off, and it didn't work, of course, and he brought it in and we looked at it and kind of tried to keep from laughing and told him it was hopeless. We also sold that. We'd sold the Kim one and we sold the Apple one. Neither of those really sold. We sold the Apple II, and there's a huge difference here. That S100 bus was a horrible thing. I mean, it didn't take into account bus loading, and so my S100 machine, which had 22 circuit boards in it, just would crash. And like, while the Apple II is this beautiful thing, it's using DRAM, it's got switching power supplies. But you know, this is the beginning. I have some artifacts of actually 4 of the boards for my machine that I'm happy to show later. My processor was a Z8000, so we're getting up there, 8,500 transistors, 4 micron NMOS. And then I go to college. I went to Northwestern for a while. I dropped out, and I spent a lot of time studying computer architecture. These are 4 of my favorite books from that era. My best friend from high school went to Caltech and got to take the early Carver-Mead classes, which I was just super jealous about. And then I got a job in Chicago working for a company called Mark Williams. Mark Williams cloned Unix, like clean room clone of Unix. I was at best, junior programmer. I contributed bugs to Coherent more than anything else. But this was a group of extraordinary people who I learned an enormous amount. And as it turns out, and they also had a PDP-1144, which like all 8 of us programmed on at the same time, which is kind of amazing. One fun thing about the PDPs was that the schematics were there, and so I took them home and I spent a lot of time studying that. But I bring up Mark Williams because it was the way I got to Commodore. Mark Williams, the head of Mark Williams, Bob Schwartz, provided Coherent, which was their Unix clone, and it was the basis for the C900, which is the first machine I worked on. The C900 had been started before I got there, and when Jack Trammell left to take over Atari, a bunch of engineers left with him, and some of them were not C900 people, and so that was how I ended up there. C900 was a Z8000 based machine. The reason it's a better machine than the 68000 for Unix because it has segmented addressing, which you just need for kernel user space separation and things like that. It was designed to be high resolution graphics, and it assumed a hard disk. I should say, just as a comment about Mark Williams, they were in the race to provide the operating system for the IBM PC. When I was there, we had an IBM PC prototype. They had Coherent running on it, but since it's a preemptive multitasking system, it just couldn't run off of floppies well. And so they couldn't demonstrate a viable operating system running just off floppies. But they did have basically Unix running on the PC. And then I was hired to do this custom graphics chip. And I had never designed a chip before. And everything I knew about hardware was from studying schematics that had TTL chips in them. Everyone who's done TTL has this book. But VLSI and TTL are really different. And what I knew about VLSI was from reading this book and trying to absorb it. It's a beautiful book, still a beautiful book. And I mixed the two up. I didn't understand what VLSI was really about. And to try to give an understanding of that, if you take something like video refresh, you generate these sync signals. Some of them are very slow. They're like at 60 hertz. Some of them are a lot faster, at say 1,000 hertz. Some of them are generating address lines for getting the data to drive the screen. Those might be in the low megahertz for say 1,000 by 800 screen. And in TTL, you would do that with counters because that's what you have. You look up in the TTL data book, you find counters, you make a big long counter, and everything falls out of that. And I presented that design as my first, here's what I'm going to do to the VLSI people at Commodore, and they all looked at me like I was crazy. And the reason is because in VLSI you use an ALU and registers because a counter is an ALU, and I just made the world's biggest, most inefficient use of a gigantic ALU. So that was it takes a little while to figure out, but it's not that complicated. You realize like, oh, inside a chip, communication's very cheap, which is very different from TTL. So the motivation for the 8724 video chip was the first chip I worked on. It was the Sun 1, which had a one-word blitter that I was familiar with. The Xerox Alto, which this paper I took or carried around with me for years, is one of the most beautiful pieces of hardware I've ever seen. It's also one of the most important machines ever made. It's, you know, overlapping windows came from there, BitBlit came from there, Ethernet came from there. You know, it's the prototype for the Mac, really. And then when I was at a company right before Commodore, which was a company called Tecmar, we actually had a prototype of the Mac because Tecmar did the first hard disk for the Mac. So I came in and I'm like, you guys should have a two-dimensional BitBlit in hardware. And that's what this chip was gonna do. It also needed to do the graphics refresh, and this doesn't sound hard, but it needed to have a mouse controller, which is a trivial piece of hardware, but we ran out of pins. And so we had to sample the mouse quadrature signals using the video sync signals, reading them backwards. So during horizontal sync, we thought, well, we'll just sample it then, because I think it was a 64-pin chip. This is a block diagram of the chip. This chip never got finished, in part because the C900 got canceled. The C900 got canceled, I would say principally because we bought the Amiga, and all of the money went to the Amiga. The Amiga caused an enormous disruption within Commodore. Like half of the engineers at Westchester got laid off shortly thereafter, I would say. I'm forgetting the dates. And so I had to find a new job. And I ended up working on the Amiga 500. So in the Moore's Law world, this is probably 200,000 transistors. 68,000 of them are the 68,000. The rest are the Amiga chips. That might be an overstatement by a little bit. I'm not counting DRAM. But, you know, this is a lot more than 1 or 9. The Amiga 500 was, you know, an attempt to take the Amiga 1000 and simplify it, because the Amiga 1000 internally was very complicated. It had multiple layer circuit boards. And, you know, what am I talking about? Okay, so a group of 3 of us basically, and Bob Russell for a while, so Jeff Porter, George Robbins, and I sat down. We actually looked at the Atari machine. We looked at the Amiga 1000. Jeff Porter really took responsibility for how am I going to get this in a Commodore-like case. So if it looks like a C128, that shouldn't be a surprise. It's the kind of thing Commodore knew how to make. You know, we went to a brick power supply. We made as many changes as we could to reduce the cost of it. And my job was to work, George Robbins and I, to restructure the system board. And that principally ended up with Fat Agnes and Gary removing the writable control store in the A1000, if you know what that is. this is a picture I found in my notes of the early Fat Agnes drawings. And in the bottom, what you're seeing are like me adding up the cost of TTL chips that we're trying to get rid of, if I'm interpreting my notes there correctly. And that was the level we were at. We were like, we need to get every dollar out of this if we can. And that was the whole point of that re-engineering. This is a die plot of the original Fat Agnes that we actually brought this to get buy off from J. Miner, who was the god of the Amiga. You know it's not a real chip because it's got actual people's initials on it, which are disallowed in all Commodore chips. And then this is the final chip with all the initials removed. That's Rev 4 or something. There's actually Dale Luck there as a young man. So we go to Hanover. It was a very nice thing. I'm not going to talk about this strange Gary bug. I can talk about that offline. So we shipped that. I still wanted a Unix workstation. I kind of felt like the Amiga could be a really good Unix workstation. I looked at Sun Microsystems as an example of something that, like, these guys were selling these outrageously expensive machines that were not more powerful than the Amiga, except for they had a little bit different graphics configuration and they could run Unix. So the next thing I did was, first we got Unix running on the Amiga. We did it first with a single gate, which I won't explain how that was made to work. It was very slow. And then I did a small discrete segmenting MMU with a friend, Rico Tudor, who was from Mark Williams. And then I thought about, well, why don't we make some chips? And so we did a 2-chip proposal, which was an MMU cache chipset. And this is the cache chip. It's a die shot of a chip I have here in a box that I can show people if they want to look at it. This never got finished. I'm forgetting why. Again, I'm still not the best at navigating how you design chips. It does lead to something in the future at Apple that's good, for me at least. And then the last product I worked on was what became kind of the accelerator board for the A2000. I did the first version of that, and then Dave Haney took that over. In here you see the top big chip pieces are actually a 68020 with Motorola's MMU, Motorola's floating point unit. And this is Dave Haney's version, so that's the thing that shipped. One thing about Commodore, one of the beautiful things about Commodore was they had their own fab. And that was really, really cool. It was amazing to work at a company where there are layout people and there are chip designing people, and you just learned so much about how chips got done. But Moore's Law is like this tyrannical thing, is that the only way Moore's Law works is if you keep up with Moore's Law, right? Which means that if you own a process technology, if you're creating chips and you're not upgrading your plant, you are not following Moore's Law. And that's what happened to Commodore. They got to a point where they're at 1.5 micron, I think, and they're stuck there. And they didn't go beyond there. And so then it becomes a burden to you because your competitor may be licensing their chip, as we'll see ARM did from LSI or some other third party, and they're following someone who's following Moore's Law. And so it became, to me, personally clear that, like, there was this weird limit on how many transistors you could get onto a chip at Commodore. And so ultimately, I wrote a proposal for like a next generation Amiga. I have to say, when I read this now, it reads like kind of an angry person who wants to control everything and wants to do, but it was me really realizing I didn't have a future there. And so I went off to Apple. Before I leave this, though, I found this crazy letter in my notes that was sent to Gerard Bucas, who was my boss, and it's, hey, you should look at this ARM processor from Acorn. And I don't remember this letter at all, but you'll see the Acorn logo in a minute. So I went to Apple in 1988. Steve Jobs had pretty much just left. I went there because Dan Ingalls was there, the co-inventor of Smalltalk, and the guy who hired me said, you'll work with Dan Ingalls, and I was all excited, and I get there and Dan Ingalls leaves. And then the guy who hired me leaves to go start the research and development for Apple in France. Apple at that time was a strange company. Steve Jobs, I think, invented this idea of like killing your parent, which was when the Mac came out, he hated the Apple II at that point, and he wanted the Apple II to die in spite of the fact that it was making all the money for Apple at that point. Every project at Apple when I was there was trying to kill their parent. There was a replacement for the Mac OS. There was Newton, which I worked on. There was General Magic. There's just this litany of projects that were thinking what you do is you make the next thing, and the previous thing, dies and withers away. We actually made two Newtons. The first one no one knows about. It was a tablet computer. It had dual AT&T CRISP processors, which is actually a beautiful processor done by, I think, Joppy, who ended up going to do Spark processors. And then I think he just did the Google tensor chip that uses systolic arrays. It had a primordial version of Wi-Fi. It's interesting to think that Wi-Fi seems so predominant, but at the time, there was no Wi-Fi. We had a guy in Newton whose sole job was to try to find spectrum that worked all around the world, because it's a standardization problem. And we wrote apps in this language called Dylan, which was a Lisp variant. So it's a case designed by Giugiaro, which was fun because he was amazing. And it never shipped. This is the product I worked on. This one shipped. That's a picture of one I have here, which I'm happy to show people later. It has the ARM 610. It had infrared. We programmed in Newton script, which is a variant of a language called Self that was done at Stanford. This will come back later because it turns out JavaScript is a variant of Self, which is kind of interesting. PCMCIA expansion. So we were really interested in languages because in that era was kind of the boom of object-oriented programming, and we wanted like garbage collected languages that could support UI programming easily. And, also instead of using files to store data, we had a persistent object store, which actually is a kind of modern idea, I think. So we spent a lot of time thinking about languages and how to use them. My job was to do the OS kernel, and so for that we were trying to get, so you have to put this in context. Newton had 640K of memory, which included whatever persistent memory you had, and it had a ROM. And so memory was outlandishly valuable, and so anything you did, you had to figure out how do I minimize the cost of that. So we ended up using virtual memory a lot to save stuff. We compressed code and decompressed it on the fly. We had stack growth that was in 1K chunks instead of 4K chunks, a lot of tricks that were done. We also wanted very fast context switching because we wanted people to just be able to use threads as often as they wanted. In the Mac, there's this big event loop, and everything gets tied into this event loop, and the code gets super weird and complicated when you are trying to print simultaneously to talk over the network and do that. So it was hard to get UI people to use threads, but we did eventually. So probably one of the most fun things we did was create ARM, which was an unexpectedly surprising. There's the acorn icon. This is a notebook from probably my second trip to ARM. And the reason ARM was appealing was that they actually understood something that surprisingly no one else did. We talked to Intel, we talked to AMD, and we said, how many MIPS per watt are you going to give me? And they looked at us like, what are you talking about? You know, we have tons of MIPS. Why do you care? And we're like, it's battery powered. It's a battery powered device. And they just wouldn't have anything to do with it. They had no idea that, like, why would you want to do that? We have, you know, so many MIPS that why should you care about the watts? ARM had this incredibly simple RISC processor. And so it intrinsically had really good MIPS per watt because there weren't any transistors there. But to their credit, ARM understood that advantage and they kept it. They, you know, to this day, they take that part very seriously, that if they own MIPS per watt, they own the portable device. And you know, the history shows that out. These are just some notes. This was, so my contribution to the first ARM was, the first ARM that ARM made, of course Acorn had 2 ARM processors before then, was adding an MMU, because, hey, I love MMUs. This is the first diagram for it. This one never, didn't come out this way because ARM didn't like, I had a reverse lookup table. They didn't like it that way, so we went with a more traditional one. This is from the ARM manual of, I don't need to explain this. The only things to note are that the little guys, AP0 through AP3, was our ability to actually protect at a subpage level. So we could actually granularly hand out 1K chunks of memory. And we made very good use of that. And then the second part is there was a thing called a domain control register, which that ROS was a single address space, and the domains allowed us to protect different parts of that single address space. And by switching those 4 bits, you could switch instantaneously between 16 domains. And that was the way we did, say, kernel user protection. This is a picture I took of the ARM 610. So now we're at like 360,000 transistors. Of course, Newton failed. And one reason I kind of think about is that Newton predates the web. It's like, it's hard to imagine now a thing you'd hold in your hand that you wouldn't want to communicate with other people with. And we spent a lot of time trying to think of scenarios of interaction and using the IR to tap and hand off business cards and crap like that. But really, if a couple of years had gone by, you would have had the web and the machine would have been, I think, a much more useful device. The second is we completely screwed up handwriting. And that was a profound reality distortion field we had. We had one guy working on it. He wasn't a scientist who understood this problem well. It didn't work well. It worked well for his handwriting. But, and somehow we got it in our head that, okay, it's just gonna be okay, and it wasn't okay. We also lost the opportunity, we could have bought the Palm Pilot solution, and because that was the first thing they used was the Newton. In any event, that was very disappointing. ARM ended up paying for Newton easily because Apple owned 1/3 of ARM. Olivetti surprisingly owned 1/3 of ARM. And then the long-term effect of ARM is kind of a consequence of Newton spinning it out of Acorn. I'm not sure ARM would have existed without Newton, so it's kind of interesting. This is a weird picture I found in my notebooks. This is from April 1992, and it's me imagining a Newton of 2001, which is apparently Google glasses of some kind, but in any event. I left Apple pretty much right after we shipped Newton so that I could take advantage of this great new product. And what we did is we decided what our product should be is mobile client server over packet cellular. So we wrote a TCP/IP stack, which is a pretty good thing, and we put it on Apple, and we had an NT server, and we had this primordial cellular packet thing in the Bay Area that ran on it used the spectrum of the power companies, and some guy had done a cellular switching network where the power company said, you can use our spectrum if we get to use it for free. And it was cool, and we could do like SQL queries over, the Newton. But of course, the Newton failed. And packet cellular, which we thought was going to show up in 1996, didn't show up till way later than that. And so I tried to get my partners to pivot to this thing called the web. And they didn't want to do it. And I had imagined, gee, if I had a scripting language in a browser and I had my server, I could like do a web app kind of framework. And that's why I went to Microsoft. I went to Microsoft and I said, I want to put a scripting language in your browser. And they said, okay. And that's the next thing I worked on. Microsoft was almost the opposite of Apple. Microsoft wanted Windows to be everything, and the web was a nightmare for them because they couldn't put a Windows stamp on the web, and they couldn't find a way to control it. And so there was this huge tension within the company. We were barreling forward on IE, and there were other parts of the company saying, why are you even doing that? Which was kind of an amazing thing to watch. So I owned the IE scripting system. And what we were after there, first of all, was to be compatible with Netscape. Netscape had all the market share. They had all the mind share. We just decided the only way to compete would be to be as compatible with them as possible. But when we did the scripting, we kind of did some things that were interesting and useful, it turns out. One was we modularized the JavaScript engine, and we also had a VB script engine, so that you could just instantiate one, feed it some objects that constituted the context in which you were operating. So in the case of the browser, it's the browser's object model. And then, the scripting engine's now running in a context. The second thing we did was we decided, gee, no one's testing their websites against Internet Explorer, so why don't we give them a free debugger for JavaScript, and then maybe they'll use our browser. Because it was the first debugger for JavaScript that was shipped, and it worked. People were like, geez, this thing's great. And so suddenly people started testing inadvertently against our browser. And the third thing we did was we cajoled Netscape to standardize JavaScript. This is the spec I wrote for our version of JavaScript. And there's a kind of long and very peculiar story that took place at the Stanford Motor Inn, where Microsoft, ECMA, which is the standards body, Netscape, Welland were in. Netscape's like, here's our standard. We presented this standard. And by the strange quirk that ECMA uses Word, the standard ended up starting with ours, which Netscape was mortified by. It turned out fine because it's a collaborative thing. In any event, one of the nice things about having modularized the scripting was that it was immediately used in other products. So Internet Information Server from Microsoft was literally I'm going to take the scripting engine, host it on a server side, and present an object model that allows them to generate HTML. They also did a shell with that. I had nothing to do with those things. They magically showed up. The reason we were able to write a language spec is it turns out JavaScript and Self are super similar. And so I happen to know a lot about Self by then. So this is where things get weird for me, is that the tension about the web has grown a lot inside Microsoft in the later 90s. And the server-side people are saying, oh, we don't need the web. We are going to grow like mad with SQL Server and these other things. And we had started a project. Actually, we recruited Steve Capps, he was one of the original Mac team members. He wrote the Finder in the Mac. He was the main architect of the Newton user experience. And he comes to Microsoft, and we decide what we'd like to do is turn the browser into a first-class application hosting framework. Because the browser it's missing a lot of things. It's missing the ability to store transient state, it's missing documents, it's missing security, it's missing a lot of things. So we spent a couple years working on a thing called Red Shark that tried to make an application model out of the browser. What happened with that was the entire management chain below the internet disappeared, because they lost the fight within Microsoft about what the future was. And I kind of think Microsoft made a very serious error there. I mean, you look what they left on the table in the end. They didn't see Facebook, they didn't see search engines, they didn't see a lot of possibilities there. So when I left that, the last thing I worked on at Microsoft was going back to my operating system roots, was a project called Big, which was, we had a lab with 1,000 very inexpensive PCs, and we thought what makes writing applications across a very large number of nodes is that there's no operating system that's managing the resources of those nodes. And there's no easy way to do it. If you looked at the way web apps were written in server-side apps in that era, you'd see these big pictures people had drawn of physical resources that they were designing. And if you ask someone, like, is this up to date? They'd say, no. And then you'd say, well, who knows what the actual configuration is? And they'd say, Joe does. And you realize there was no dynamic ability to manage those. So what we did is we made a version of NT that was 5 megabytes. We could send it to a bare node. We could then load any code onto it we wanted. We had scripting object models for switches and routers so that you could configure the communication within the network. And then the last idea that was kind of a nice idea is if you look at a large server-side web server, what you'll see is a fairly small number of different kinds of nodes, but they're at enormous scale. And so the idea is a thing called the scale invariant model, where you say, well, if I take all the scale away and I just program against these abstract nodes, then I can say, oh, the load on the front-end servers is growing, and so I'm just going to add more servers to it. And so we ended up with a programming model for that. That actually shipped in the dev tools. I had other adventures. I'm going to stop there because I've probably talked too much. But and I'm happy to answer questions if anyone has any questions.
We'll come to you.
How come the Mac never had any hardware acceleration for video? Or for, for Blitter or anything like that when it first came out?
That's a really good question. Actually, no, I have a good story about that. When I first got to Apple, they knew I'd worked on the Amiga 500, and they came to me and they said, can you tell us how much those chips cost for the Amiga? And I said, I can't do that because I didn't really think that was right. So they said, can you look at this competitive analysis that we've written? And so I looked at it, and their estimate on the Amiga chipset was, I think, $120 for the chipset. And if I'm remembering correctly, it was $14, okay? And that was the first time I realized, like, oh, these guys don't know much about chips. And it was true at that time. At that time, there was very little chip design going on at Apple. I mean, we did a little bit of it in Newton, but mostly ASICs for, just glue logic and things of that sort. There was a processor design thing in there, but it was in research. Interestingly, there was a chip, a graphics chip, that they were working on, which was kind of an interesting idea, but the guy who did that went off and founded Web TV and did very well doing that. So I think there wasn't a built-in culture. That was the biggest difference between Commodore and Apple. Was Commodore was chips at the core. Everything I worked on was like some chip, and and the only sad thing is that I wish we had had a better process to work with, because you could have done more stuff.
Any other questions? Well, I want to thank you, Bob, for
Sure.
coming by today. Everybody give Bob a big round.
All right, big hand for Bob.